Hello, everybody, and welcome to this month's Department of Energy Python Exchange. My name is Cameron Riddell, and I will be your host this evening, afternoon, or morning, of course, depending on the time zone that you live in. As you all may know, our goal here is to have Python thrive within the National Lab system and the associated research sites. And in support of that goal, we are joined by our guest panelist, Kyle Chard, who is a research associate professor in the Department of Computer Science at the University of Chicago and also holds a joint appointment at Argonne National Lab. Kyle will be sharing about a distributed function as a service platform that enables flexible, secure, scalable, and high-performance remote Python function execution called Globus Compute. But before we go into the agenda and introduce all of our panelists for today, I wanted to remind everyone here about a few key points of these exchanges. This call will be recorded, edited, and posted online. As a consequence, I want you all to be conscious of the information and the questions that you may ask to ensure you're not accidentally sharing anything that might be privileged or requires clearance. Additionally, we are a growing community, and I would love to have the ability to stay in touch with every one of you. And if you want to be kept up to date with our monthly exchanges, please sign up for our mailing list, which you can find on our website, meetup.doepy.org. You can additionally find recordings of not only today's exchange once it's been edited, but every Python exchange that has been run in the past over the last 3 years on this website as all. That is meetup.doepy.org. Now, for those of you who have never joined us for an exchange, I'd like to share with you that we typically break these event downs into 4 parts. First, we'll introduce our fantastic lineup of hosts and guest panelists so that you can get to know each of them in their respective fields and backgrounds. Second, we'll kick off into a coding activity where we'll ask some very applied questions to our panelists to elicit some practical discussion about best practices in software development and where they fit into the world of an academic or a scientific researcher. Third, we will turn things over to our guest panelists who will share some prepared remarks on Python. And finally, to wrap us up, we will have a full discussion about the points brought up by Kyle. And for everyone joining us in our audience, this is your chance to ask questions and engage with our panel to help us all understand how we can use Python better and how we can use Python to do our work better. That is, of course, our scientific research. Now, let's go ahead and jump right in to our introductions. And for our introductions, I like to play a little game called Ask Me About. And so I'm going to introduce our host panelists, followed by our guest panelists, and I'm going to ask them a question. And that question is, well, Cameron, what do you consider yourself to be an expert in? And what types of questions would you like to hear from the audience today? And so let's go ahead and start our little game of questions. Like I said, we'll first start with our host panelists, and ironically, I will start with myself. So hello, everyone. My name is Cameron Riddell, and while I'm not affiliated with a specific laboratory, I do have a background in academic research as I studied cognitive sciences in graduate school. For today's exchange, I would love to discuss any and all questions related to Python as a whole, or specific concepts and uses in Python's vast scientific computing ecosystem relating to tools like NumPy, Pandas, Matplotlib, and more. And with that being said, why don't we jump on to our first host panelist aside from myself, that is Tom Caswell. Tom, I see that you're affiliated with Brookhaven National Lab. Can you share with us what you consider yourself an expert in and the types of questions you want to hear today?
So hi, I'm Tom Caswell. In addition to my role at Brookhaven, I'm the project lead for Matplotlib, and I'm happy to take questions about plotting and visualization in Python and how to manage a large open source project.
Excellent. Well, Tom, you have a plethora of Python programming experience, and not just Python experience, but integrating that experience and knowledge into members of your team as well. So we will definitely be asking you questions on that, and I'm very happy that you're here to join us today. Next up, we're also joined by Dylan McReynolds. Dylan, I see that you're affiliated with LBNL, and can you tell us a little bit about what you consider yourself an expert in and the types of questions you want to help us answer?
Yeah, I would say my expertise is in building applications from disparate frameworks using web and database technologies. And I would love to hear questions about Python in the web or Python in database.
Fantastic. Well, Python in the web, I believe, is a good chunk of what we'll be talking about today. Maybe not as some type of front-end component, but we'll definitely be talking about Python. We'll definitely be talking about web. So Dylan, thank you so much for taking the time to join us today. Next up, we are on to our guest panelist. This is our person of the hour. We are joined, as I said earlier, by Kyle Chard. And Kyle, I see that you have a joint appointment with Argonne National Lab. Can you share with us and our audience what it is that you consider yourself an expert in and the types of questions you want to hear today?
Sure, yeah. Hey, everyone. So my research area is really distributed computing, and we have a really strong focus on scientific computing, so scientific applications that drive interesting distributed computing problems. In terms of questions, I work generally in workflows, so anything related to workflows, parallel and distributed computing, and also research data management as part of the Globus project.
Excellent. Well, Kyle, it is an honor to have you here with us, and I'm very excited to hear your prepared remarks. Before we jump into that, here at the Python Exchange, we love playing a very brief game, or I should say, an activity. Today, we are going to have a coding activity, and it's titled, When Do I Use? So let's see how we play. Well, here's a fact. Python's open source ecosystem is absolutely massive. And as Python's varied tooling grows, we've seen numerous different attempts at tools that occupy an overlapping problem space. So today, we'll work together to determine when and why we should use a specific Python tool. The rules for our panelists will be, well, we're going to present you with many existing tools that all share a similar problem or all cover a similar problem. We'll provide guidance on whether there exists some logical steps to decide when to use each of those tools, or if one tool truly does rule them all. And finally, we're going to be scored on specificity with bonus points for relatable anecdotes and experiences working with scientific researchers. We won't actually be scoring you, but personal anecdotes are always fun. And so let's go ahead with our very first round. In this round, we'll be focusing on data frame libraries. In the last about 5 years, we have seen an explosion in the number of data frame libraries, and they can't all be useful, can they? Pandas is, right, our OG of the squad here, so the original data frame library, at least in Python. And now there's other things like koalas, Dask, and polars. And so I'm curious for our panelists, any guidance on when I should use pandas and say, you know what, the original one is the one that I should keep using? So I saw Tom come first.
So I would reach for pandas in cases where my data can definitely fit in memory on my machine. And I want to have it up and running with a minimum of additional machinery and work to get going. I just want to import pandas as PD and start reading CSV files or whatever I have. Whereas if I had data significantly bigger than my memory, or data that I needed to scale horizontally the computation, I'd probably reach for Dask. I guess I'm not sufficiently familiar with quals or polars to have a good answer there, but from quals being PySpark.pandas, I suspect if you have PySpark already, or if you have Spark already, you should reach for the tool that leverages that existing machinery rather than trying to shoehorn it into a different data frame library.
Definitely. Those are all fantastic points. So it sounds like Pandas is going to be your Swiss Army knife, right? If it fits into your RAM or fits into your memory, Pandas should be able to analyze it, whether it's a CSV or if it's coming from JSON or if it's coming from actually a lot of different file formats that Pandas handles for us. Dask for a distributed data frame. So if you have something that won't fit into memory, definitely reach for that. And PySpark, well, if your company or your university already uses Spark, then you should probably use PySpark since that's where the data live and you should meet the data where it's at. So we have this outlier polars. And Kyle, I'm curious, did you have anything additional or anything that you wanted to add for our discussion here?
No, I would agree. I mean, we use a lot of pandas, obviously, for local data frames, the de facto standard, I think, for data manipulation, management, and structured data in a single machine. Obviously, at Argonne and other distributed computing environments, Dask is our go-to to scale those pandas applications. I mean, they implement the same APIs of data frames, so it's very easy to go from a pandas environment to a Dask environment to scale up your analyses. And Dask also does a little bit more than just data frames, and they have the Dask distributed library that allows you to run other types of applications as well. I don't know much about koalas and polars, so I don't think I can help there. I assume that koalas also would give you some of the DAG-like processing, the workflow type model that Spark provides. But again, I haven't used it, so I can't speak confidently about that.
Fair enough. I think that's a great synopsis, especially with the additional text there on Dask for things like, I know you can do like distributed NumPy and D arrays and distributed other types of very familiar, right, Python containers. Now, for polars, I am a resident user of polars, and I quite like it. It occupies almost the exact same space as pandas. Now, since pandas has been around longer, it's going to be more feature complete. But the thing that polars is designed to do, and it's designed to do it in a way that pandas can't, is polars is a object-oriented interface where you're actually building queries when it feels like you're seamlessly just working on the data frame itself. So you're building queries, and then you can actually have those queries be lazily evaluated. And so what it does is it runs an optimizer over the query plan that you have built with your code to ensure that your code is running at least as fast as your logical plan allows it to. And so it's effectively a lazily computed pandas that can speed up a lot of your pandas operations. If pandas is a Swiss Army knife of desktop analysis where you're just working on a laptop and you want to see quick results, polars can occupy that same space, but polars is also going to be more suited for building robust data pipelines just because of how it adheres to some data frame, like having a strict schema and things like that. So polars is going to be a little bit more pipeline favored. Now, one thing that polars can't do, right, is distributed computation. It does leverage multiple cores, but it can't horizontally scale across multiple machines as far as I'm aware. And so you will need to rely on things like Dask if you want true horizontal scaling in that aspect. So polars is the shiny new tool, not as feature complete. So that's my synopsis. Dylan, anything to add on top of these? Or you think we've covered a lot of the points here?
I was only going to say, I just learned what polars was, so thank you for that, Cameron.
Yeah.
And it's interesting, it looks like it occupies a very similar space to DuckDB, but a little more data frame centric. And it's interesting to me that the world is sort of coming back towards SQL and queries and optimized query plans and things like that. It's the more things change, the more they stay the same.
Yeah. I'm very happy you brought up DuckDB. I was holding myself back not bringing it up because I also do really love DuckDB. And since they all use the Apache Arrow memory layout under the hood, polars builds on top of the Arrow layout. So it's some extensions that won't be available in things like DuckDB. But you can have actually zero copy transfer of these data frame tools. So if you're using DuckDB and you're using polars, you can actually evaluate DuckDB code on polars data frames, and there should be a zero copy overhead on that, which is actually quite nice and quite convenient because DuckDB does offer some features that polars does not yet have. My favorite being inequality joins, or optimized inequality joins, I should say. Tom, you came off mute. Did you have anything to add there right at the end?
I was going to ask a question. Just how does IBIS enter into this then?
So IBIS, I've actually never used IBIS, but IBIS sits above. It's kind of like a meta data frame, right? Where they give you some type of uniform data frame-like API. I'll use that term very in quotes. They give you some data frame-like API, and then you can actually have it evaluated on pandas or evaluated on polars or on any of these backends that we've talked about. Now, my concern for tooling like that is if you're creating a uniform API, you're going to lose some of those features that make those underlying tools unique. And so since I've never used it, I won't talk about corner cases where this doesn't work, but I will say, if you're just looking for one kind of syntax that you can evaluate maybe on your local computer with a pandas backend, and then send it over to your DevOps people to go have it be scaled to Dask without much concern, then this could be a way forward for you. But as I see it, right, IBIS kind of sits above all these since it's not trying to compete with them. It's like a plug and play backend kind of idea. All right, well, that takes us to the end of our first round. Let's jump into parallel and concurrent execution. So we've talked a little bit about distributed software. For concurrency and parallelism, we're talking about two common ways to speed up your code. We have many built-in third-party tools, or I should say built-in and third-party tools to achieve this mode of performance in Python, but when do I actually use each one of them? So we have async IO, threading, multiprocessing, joblib, and concurrent futures here. And I'd love to open this up to our host panelists to see, do you know one of these? If so, when should you use it?
I jump in first again.
Yeah, go ahead, Tom.
I'm going to say the first, given all currently released Pythons, the first thing you need to sort out is if you expect to be CPU bound in Python or not. And that's the first decision point. So if you expect in all released versions of Python, there's the global interpreter lock, which says only one thread can be interpreting Python bytecode at a time. And so if you expect to be spending most of your time in Python doing work and you want to parallelize, then you need to go to one of the tools that will spawn multiple processes. So that way each process gets its own lock and they can run truly in parallel. The cost of this is now you have a process barrier, so the serialization of getting data from one process to another can become a big bottleneck. And you can sometimes spend as much time on that as you do on your compute. However, if you expect to be doing things concurrently, where you are most of the time waiting for like network IO, then something like async IO or threading or things that are running multiple tasks within a single process makes sense, because C extensions can drop the GIL, and all the low-lying underlying IO libraries will drop the GIL when they go into a wait for, like, please wait for the socket or please sleep. So if you're going to have many mostly idle tasks going, either threading or async IO will work well. Threading is kind of the original thing that makes sense, that is widely used. However, it's a preemptive multitasking, which means at any point, any of the threads can take over and start doing things. And so if you have shared resources, now you have to think about locking, and this can be a difficult and problematic task. On the other hand, async IO is a cooperative multitasking where you thread the individual execution tasks are only interrupted when they yield control. In modern Python, using the await keyword, which gives you more it's easier to reason through when things are going to step on each other, because you're no longer saying I can be messed with at any time. You're trying to mark sections where I don't want to be messed with here. You're saying this is a point at which I can be messed with, and you can plan around those. In addition to async IO, there's also Trio, which is a different executor that's based on the same idea that provides a slightly richer set of primitives. And I guess a variation on threading is if you have significant code that has heavy compute written not in Python, you can get away with threading because it can release the GIL, and then they can all run in parallel.
Yeah. Now, Tom, I have a question for you on that end, but I want to make sure for our audience, can you evaluate this metaphor that I'll lay out? Because we've mentioned preemptive concurrency, cooperative concurrency, as well as parallelism. The metaphor I like to use is working in a kitchen, right, as kind of kitchen staff or chefs. For our parallelism, well, you just have two chefs, and they can do all of the tasks independent of one another. That's our parallel. For our cooperative concurrency, that's imagine if I had laid out a step-by-step recipe, and then now I say, okay, I'm going to go in, I'll start boiling the water, but while the water is boiling, I can step away. I'm going to go chop vegetables. Once the vegetables are done, I'm going to go do something else. And you plan it out when you're going to leave what task and when you're going to come back to each. Now, our preemptive, where our scheduler or operating system is in control, this is kind of like it's very similar to the cooperative, but I now have a kitchen manager telling me when I need to switch tasks. And so that's kind of the idea here. Do you have one chef? If so, are they in control of how much work they get done before they move to a different task? Do you have two chefs, or do you have a kitchen manager telling you where to go? But with that in mind, Tom, my question for you was, you mentioned that if we have libraries that relieve the GIL, right? So libraries implemented in C, are there any concerns, right? If I'm using something like NumPy, and I try to launch a NumPy operation in a thread, and it's using, say, a dot product, which is going to tap into OpenBlast or something like that. Is there a concern there about who actually controls the thread pool?
Yes. If you have multiple layers that are going to try to auto infer how many threads they can use, it is easy to oversubscribe your processors, because each level that does not know about each other says, I see 20 cores, I will make 20 threads. Then each of those 20 threads launches something that only says, I see 20 cores, I will launch 20 of my threads.
Yeah. Very fair. So threading for kind of compute-bound things, it can work, but it can also be a foot gun in the future.
Yes.
Excellent. Now, Dylan, I saw you had come off audio just a moment ago. Did you have something additional to add here?
Only that just as a general rule, especially for like web-based applications, I really like cooperative concurrency as a model. It really tends to make it's an easier programming model to think about, although it contains some gigantic foot guns in that it's very easy. And I've seen code bases that fall into a trap of not of doing things that are that take time but aren't in an await, which it results in sort of in locking out the entire Python process that's trying to do work. One note, a classic example is the FAST API library, which is almost omnipresent now, which makes it super easy to not care whether you're using a thread pool or an async operation. And it's almost too easy to get into a trap of not awaiting on things that take I/O, for example. And I think it's just something that people really need. It's a great programming model, but I think it's something people need to be very cautious about. And I would generally, like, for example, in FAST API, reach for async await if the I/O libraries that you're using are themselves async, and not using async if the I/O libraries you're integrating with are not async.
Yeah, absolutely agreed. And I think another point there is if you have synchronous code, right? Code that just runs top to bottom, and maybe there's function calls in there, but everything has to wait until the end of the previous line's execution before the next line is executed. That's our synchronous code. If you have to take that type of code and turn it into something that operates concurrently, so maybe introducing some delayed calls or some tasks that are handled in the background while the main program continues, that rewrite of that code base is going to be much easier to do if you initially do it with threads. So going from synchronous code to threaded code is a much smaller lift than it is going to be from synchronous code all the way to littering your functions with async and await everywhere. Now, use the term littering softly there, because I do really like async IO and async and await.
Well, and I agree with that entirely. And it's especially true given that you would often end up having to change your database driver or your HTTP client driver or whichever. A lot of your third-party code would have to be asynced before you would be able to make that refactor happen.
Yeah. And it goes all the way down to function coloring, which I'll leave for our audience to give a Google. I think that's a good one. But Tom, final thoughts?
This reminds me of adding constant correctness to a C++ code base. I will edit one place. Oh wait, I touched everything.
Exactly. All right, so with this discussion wrapped up, let's head to our final round on statistics. So for statistics in Python, we have a couple of tools. We have the built-in statistics module. We have stats models, which was originally part of SciPy way back when, and it branched off into its own things. There's scikit-learn, which was, or I think still is, kind of the de facto traditional machine learning library in Python. And of course, there's SciPy, which is SciPy just it's a grab bag of statistics, in my opinion, but maybe somebody else can make a little bit more sense of it here. So I'll open up for our host panelists. When should I use any one of these over another? I know for one, the built-in statistics module, if I don't want to ever import NumPy into my project, built-in statistics, if I have a bunch of numbers just in a Python list, statistics is absolutely the way to go if it covers your use cases, right? So you can do things like very basic statistics. I believe it can sample standard normal distributions or just Gaussian distributions in general. But you can also do mean, standard deviation. Not certain if it has skew and kurtosis, but it has a couple of handy functions in there for pure Python use. That leaves stats models, scikit-learn, and SciPy, which are going to cater especially to our numerical arrays, our NumPy. Any thoughts on any of those three tools from our hosts?
I would say I'm not an expert on these tools, but the way I've used them before, scikit-learn very much for machine learning algorithms, particularly pre-PyTorch and TensorFlow, although we still use it for various types of ML algorithm. And then SciPy, as you said, a bit of a grab bag of algorithms and foundations to build scientific codes from sort of highly optimized numerical sort of capabilities through to optimizers, etc.
Mm-hmm. Yeah. So the way I see that, scikit-learn, right, you just hit the nail on the head, traditional ML stuff using NumPy arrays and things like that under the hood. And recently, pandas now, I believe. But what differentiates stats models and scikit-learn for me is, do you care about what the p-value is? And so for most of us doing research and trying to publish, we care a lot about what the p-value is. And for those of us whose job it is to predict things based on data, of course, you're going to care about the p-value a little bit, but you're probably going to be looking at other statistics, measures of goodness of fit, and things like that. How good are your predictions? And care less about the p-values, likely because you're throwing a ton of features into that thing to make the best predictions you can as possible. So that's my differentiator. I will also say if you're coming from an R background and you're used to the formula syntax, the stats models has mostly a translation of the formula syntax from R that you can actually use. It uses an underlying library called Patsy, which is an attempt at grabbing some of R's formula style syntax, which if you're a statistician should read very, very easily on the eyes, I will say. Any final thoughts from our host panelists about these tools? All right, that means we probably differentiated these tools enough from one another. And with that being said, why don't I turn things over to our guest panelist, Kyle, so he can tell us a little bit about how he uses Python. So Kyle, why don't you take the reins and I'll fade into the background here.
Okay, well, thanks, Cameron. Yeah, so I'm going to talk briefly about basically extending the function as a service paradigm that's fairly pervasive in the cloud into a model of a distributed federated function as a service platform in which you can execute Python functions across existing resources, across what we call the computing continuum, which sort of means the very broad range of distributed resources we have available to us in the DOE, NSF research ecosystems. Before I start, I just wanted to quickly introduce Globus as part of this talk. So I'm talking about a platform called Globus Compute. And Globus is a non-profit service developed and operated by the University of Chicago. We're primarily known for our research data management capabilities, the ability to manage data, transfer data, share data, increasingly into automation flows and now into managed computation. The mission of the Globus org is to increase the efficiency and effectiveness of researchers who are engaged in data-driven science and scholarship through sustainable software. Okay, so now back to the actual regular material that I was planning on presenting. So let's start with context about why we've got into this computing continuum federated functions as a service model. So I think we've probably all observed that we're seeing a big change in the way that computing resources are delivered, right? And there's this interesting quote here from a paper from Thompson and Spanuth and the communications of the ACM, talking about the economic cycle that's led to this use of a common computing platform changing into this much more fragmented world where the economics are pushing deployments of much more diverse, heterogeneous resources, right? So you're seeing innovation in terms of the types of computing resources that are being deployed, from AI accelerators, GPUs, CPUs, TPUs, etc. And as we move to this world in which we have a more fragmented, heterogeneous environment of computing resources, by definition, we move to a world in which computing resources are much more distributed. They're much more remote. It's inevitable now that I must make use of remote computing resources in order to gain the efficiency, the performance that I need for my applications. It's unreasonable to expect that I, as a researcher, will have many different types of computing resources at my disposal. We're also benefited, of course, by a few things that are happening in the computing world around connectivity. We have very rapid connectivity now. This has enabled things like cloud computing. It may be cheaper for me or faster for me to run a computation on the cloud on a specialized piece of hardware, say a TPU, suffering that latency of sending the task to the cloud, than it is for me to actually run that task on my less well-optimized CPU on my laptop. So given this environment of distribution, this is where Globus has really focused our attention over the last decade or so. Originally, we started as providing this sort of research data management across various computing resources, so where we provided fast, reliable data access and transfer. We then broadened to provide secure data sharing, so enabling people to share data directly from where it resides on your large-scale HPC resources, in one of the DOE labs, on my cluster at the University of Chicago, etc. More recently, we've moved to data management automation at scale. So you can think of this as cloud-hosted workflows, where we're enabling sequences of steps to be coupled together and organized in a graph or a sequential process of events that would happen. So think of this as an instrument acquires data. We need to ingest that data immediately, move it from the instrument to large-scale storage resources, then move that data perhaps to an HPC system where we run a reconstruction, and then send the reconstructed data back to the scientists sitting at the instrument to be able to view whatever they're processing at that time. Of course, as you just heard there, that research flow that I described inevitably includes a need for computation. And so what our focus in this talk is about is trying to deliver these same, what we call fire and forget capabilities that Globus has worked on over the last decade or more for computation. So essentially enabling myself as a researcher to outsource, fire and forget, the task of running a set of computations on a remote computing resource, anywhere ranging from my laptop or an edge device through to a supercomputer at Argonne or another location. So if you think about this need to compute remotely, we think about some of the challenges. So remote computing has been around since the dawn of computing, right? Originally, it was I would walk to my mainframe computer and walk through a door and access a terminal to be able to actually do that computing. It's remote in the sense that I had to actually physically move to that computer. Of course, more recently, we have the idea of we have SSH connections, we connect to a remote resource, we run our computing, come back again and take our results away. If you think about the challenges that impede use of this type of remote model, they're fairly broad and fairly varied. And many of these challenges really are barriers that prohibit sort of democratization of these large-scale computing resources that really are integral now for such a broad range of scientists to be able to make use of modern ML algorithms, be able to process the amount of data they have at their fingertips, et cetera. So to be competitive, increasingly, people need to use these more advanced remote computing resources. So if we step through some of the steps that you would have to go through as a new user trying to make use of a supercomputer or cluster delivered by one of the national labs. First thing we need to do is we need to authenticate. We need to often know about the specific credentials required for that machine, 2FA, etc. We then need to create a network connection using something like SSH where I can connect to that resource securely, be able to then submit a job to a batch job scheduler. Of course, fortunately in the DOE, we have 3 different schedulers across the 3 different facilities, and well, across the 2 leadership computing facilities in NERSC. So I need to know what that resource scheduler is. I need to know how to speak to that resource scheduler. I need to know, is it an SBatch command? Am I talking to PBS? Am I talking to Slurm? Am I talking to Flux? I then need to know how to interpret that I've submitted a job to a queue. I see a strange priority score beside my job. I don't know when it's going to run. I need to know how to actually scale and select the nodes that I'm going to use. I need to know how to use GPUs that are accessible on that node, etc. A next thing from the Python perspective is configuring the execution environment. And so we've seen a lot of research in academia focusing on how can we more efficiently provision Python environments across large-scale HPC systems. In the early days, of course, Python was seen as problematic for these very large HPC systems because it was inherently an IO-bound process. We had a lot of files that needed to be loaded. So if I'm running the same Python process on 10,000 cores at the same time, I'm incurring a pretty significant IO load that's going to basically cripple the parallel file system, right? So being able to think about how do we optimize and configure that execution environment such that the Python libraries I need to use are present on the remote computers that I'm using, and how do I make sure that that's efficiently loaded such that I can execute very quickly, which is sort of the whole point of using the HPC system in the first place. Of course, this is the happy case. In many cases, our codes fail. They fail because the code was poorly written by a researcher like myself, perhaps because a node fails during execution, perhaps a network connection falls over. The number of times an SSH connection is going to break when I'm trying to run it from my laptop, run a computation from my laptop, etc., on an HPC system. Being able to first identify these errors, detect them, being able to interpret what that error means, and then being able to recover from it is, of course, a significant barrier. And as I said at the beginning here, we need to overcome these same obstacles every time we move to a new resource. So when I move from an Argonne supercomputer to a NERSC supercomputer to an Oak Ridge supercomputer to my institutional cluster to the cloud, etc., I'm doing these same types of steps over and over again with slightly different approaches in each case to make things just a little bit harder. So this is where we decided to build this Globus Compute platform. So Globus Compute was initially called FunkX. It was funded by the NSF as part of a CSSI award. And as part of that CSSI award, we had this plan to sort of build out the prototype as FunkX and then transition it to the Globus ecosystem once we got to a really solid product that was broadly usable by a range of people. So you can think of Globus Compute as providing a function as a service interface for any computing resource. So you see on the picture to the left there, you have a bunch of different computing resources from HPC systems to laptops to commercial clouds. These systems provide different interfaces in order to be able to provision resources, from the common things like Slurm and PBS through to more industry standard things like Kubernetes. And what we do is we provide a programmatic interface on top of these resources, this Globus Compute agent, and connect that agent to a cloud platform that we operate to provide that single point of contact, that reliable fire and forget orchestration of a bag of tasks that we want to execute. So the benefits, of course, here are that we provide a single consistent user interface across these very diverse computing systems, enabling people to think as they do in the cloud with FaaS. They think entirely at the level of a Python programming function. They define a Python programming function. They then choose to execute that function one time, 1,000,000 times with different input arguments on one of these target systems that's deployed out there in the wild across the computing continuum, as I said at the beginning. So how is Globus Compute implemented? Really, there's only 3 main parts to this. There's the cloud-hosted compute service. We run this on Amazon Web Services. It's a highly available service. We use all sort of best practices for how we deploy that. We run it across several concurrent instances such that we can scale for workload, etc. This provides us that single API. It provides us that reliable fire and forget orchestration such that when a user tells us we need to execute 1,000,000 tasks, the compute service is now responsible for doing it. The compute endpoint, which is the other half of this hybrid model we have, connecting the cloud to the edge. This endpoint is a little piece of Python code that sits there on a computing resource and exposes it to the cloud service such that we can now execute these Python functions. And then finally, the SDK, which is the user-facing piece of Globus Compute, which enables someone, a user, to basically take a Python function, and then execute that function on a remote resource, such that I can embed this in a Python program or use it in a Jupyter notebook to run my workloads. So what does this look like to a researcher? So if we assume we have two computing resources here, computing resource A and computing resource B, they may be a laptop and a supercomputer, both of which have a Globus Compute endpoint deployed, which is this little orange thing with the spider-like logo, which represents a CPU. In the cloud, we're running the Globus Compute service there. Scientist comes along, they want to run their workload. First thing they do, they, in their Python program, they basically request a function be executed on endpoint A and B. Behind the scenes, Globus Compute, the service in the cloud, will cache that request, because what happens if A and B are offline at the moment? We don't want to lose that job and say, no, we want to just keep it. It's fire and forget. So as soon as these resources are online, we basically, the cloud-hosted service will dispatch the tasks for execution. The agent will provision resources on that computer from the scheduler, from local processors running on different cores, etc. It'll run the task, it will monitor it to make sure it doesn't fail. If it fails, it'll catch the exception. And then it returns the result or the exception to the cloud service. Again, that result is cached in the cloud for a few weeks until the user comes back at a later time and retrieves the results, interprets what they've done, and then perhaps loops and runs another set of tasks. So let's go through the main pieces in a little bit more detail, and then if I've got time, I'll show you an example of how this works. So this is the Globus Compute agent. This is a pip installable agent. It's a piece of Python code. We also have native packages for Debian and Yum. You essentially install this software once, and then it's accessible such that you or other people can create endpoints on that resource. We use the parallel programming library, which is a Python-based library, for its ability to speak to different resource providers and provision resources, and also for its ability to deploy a pilot job model on those resources. What I mean by pilot job model is we speak to the scheduler infrequently. We say, scheduler, we need 5 nodes, and we want these nodes to be cut up into 30 concurrent tasks per node. We go and deploy our software, our pilot software, on all 5 of those nodes, a worker for each of the 30 concurrent tasks. And then those workers are responsible for taking the tasks, running them, and returning results back again. So the good thing is, once I have a bag of tasks, I'm not going back and forth to the scheduler, the Slurm scheduler, the batch scheduler, etc. I'm instead using this pilot. So once I've provisioned the resources, now I'm just streaming the tasks into the actual workers running on the cores, on the compute nodes, sending results back again, streaming in more tasks to run on those cores. What does installing a Globus Compute endpoint look like? So we actually have 2 flavors of Globus Compute endpoint. We have a single user endpoint, which I'm going to show you here. This is as simple as pip install the Globus Compute endpoint, configure the endpoint, which creates a default configuration for using multiple cores on that machine. And then I can start that endpoint. The first time I start the endpoint, I'll go through an authentication authorization step where I have to log in using my several thousand supported identity providers that Globus supports. I log in once, I enter a code, I've paired these things, so now I've set up my endpoint such that I am the only person that can run a task on it. We also have a multi-user endpoint that I'm not going to talk too much about here. That's installed by administrators. It enables a single endpoint to serve many requests for different users. And basically the way that system works is a user will try and submit a task, it'll fork a process in that user space, run the tasks as that user, and then shut up shop when the workload is finished. The multi-user endpoint also has a bunch of security controls, from high insurance controls about particular identity providers that are required, timeouts for login, etc., and even whitelisting of functions that are allowed to be executed. What does this look like from the user side? So it was interesting, you talked before about concurrent futures. So we've adopted the concurrent futures API very heavily here. So basically, we've implemented the concurrent futures executor API such that we can have this asynchronous execution of tasks. So you can see on the right here what this looks like. You import the Globus Compute executor, you pass it an ID of the endpoint you want to use, which was the agent we just deployed before. I can then define a Python function. You see there I'm defining hello world, and now I can use that executor API, the concurrent futures executor API, to submit that function with arbitrary arguments, and what I get back is a future. This future is essentially a promise for the result at some point later. So we don't block our process here. We don't block our Python program for the result to execute. Instead, we can carry on with our Python program. And at a later time, we can use that future to ask it, well, are you done? Or what is the result of that computation you were running? If we call result, that's a blocking call. If we call done, that's an asynchronous, is it finished or not? And we can carry on again, right? So it's as simple really as selecting the endpoint you want to run on, defining the function you want to execute, and then executing it with whatever input args you like. And of course, in practice, you would often have a for loop around this where you'd say, for some number of tasks I want to execute with different input args, just submit, 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 keep track of all of the futures that come back, and then use the as completed part of the function as completed that comes with concurrent futures to wait for the results to come in. Importantly, the deployment of the endpoint is actually an outbound connection. So when I deploy an endpoint, it's making an outbound connection to the cloud to ask for tasks. So we don't need inbound connectivity into the computing resource to actually run that task. And as I said before, that cloud is basically buffering, caching, storing the tasks that are to be executed, and also storing the results that are being returned at the conclusion of the workload. So I'm probably a little bit slow on time here, so we'll skip the actual demo, but there's a notebook down the bottom here that you can run. You can run this without installing anything on your computer to get an idea of how this works. You basically run the notebook. We run a tutorial endpoint in the cloud on Kubernetes, and so you can use those resources to go through and test out what this looks like for yourself. You can also optionally, of course, install your own endpoint using the pip instructions on the previous slide. So of course we have these APIs. We have this REST API for all of this functionality. We have the SDK that wraps a Python layer on top of that. The other thing we provide is a web interface to be able to look at the computing endpoints that you have accessible to you. So you can see on the left there, this is a list of all the Globus Compute endpoints you have access to. So I have 84 of them. I've clearly been very productive deploying Globus Compute endpoints everywhere. And then on the right, you can actually dig into an endpoint and be able to see how it's configured. You can see how many tasks are waiting, et cetera, to be able to run on that endpoint. And this refreshes every minute or so. So we've been building this platform now for about 5 years. As I mentioned, we were fortunate to receive NSF funding around 2019. We've seen over these 5 years pretty encouraging growth. You see in this plot here with all completely different scales that users are growing every year, the number of endpoints is growing, the number of functions is growing very, very quickly, and the number of tasks, so tasks being the individual functions that have been executed. So we've had now roughly, I think we've just passed 1,000 users have actually used the system. We've run about 35 million tasks, 1 million different functions have been registered, and there are about 12,000 endpoints that have been deployed. When we think a little bit about the early adopters of this platform, so we announced a general release of Globus Compute probably about a year ago now, and we've started working with various groups or looking at usage and understanding the types of applications that are using the system. We see three main examples. So the first is, I just want to execute a bag of tasks, a number of tasks in a remote location, and I'd like to not have to deal with the SSH part of it, the managing of the tasks. I just want it to happen and for the results to come back to me. The second one is research automation, so being able to plug it into a workflow where computation is a part of that workflow. And the third is actually as a platform for building other services. So we have quite a number of people that are building portals, gateways, other types of services on top of this because they have the need to deliver computing capabilities for their user communities. So we're going to have a look at a couple of examples here of where we've used Globus Compute. The first is during the COVID pandemic, we had this need to screen a number of molecules to identify things that could be good drug candidates. Fortunately, for the only time in my life, many people offered us a lot of computing resources. So we had possibly, I think, more computing resources than we had compute work to be done, which is not something I've seen before or after. So we had this interesting task. If I've got billions of molecules I need to screen, I've got probably half a dozen or more supercomputers at my disposal. What do? We go and deploy this Globus Compute agent on each of these computing resources. We go and work to code up each one of these boxes here, like canonicalizing a smile string, computing some features that can be used for machine learning algorithms, computing a fingerprint of that molecule so we can do similarity search, even generating images because people wanted to use the images in machine learning algorithms to see if they could find characteristics that would be potentially useful. And so what we were able to do was just queue up all these things ourselves, and other researchers basically just wrote little Python functions for each of these things, and then we just submitted them off to run on each of these supercomputers, waited for the results to come back again. This is an example showing another use case we see where people are embedding AI in these bag of tasks loops. So they want to use AI to perhaps more efficiently screen a search space such that they're not running expensive simulations across everything. They run a small number of expensive simulations, train a surrogate model to predict values, and then prioritize what they do next. There's an example here. I gave a tutorial last week where we walked through how to develop an AI-based workflow for computing ionization energy, which is useful for determining battery materials that would be good for batteries. For the automation side, so we see here an example of how we use compute and automation. So this is analysis of data coming off an experimental beamline, an instrument. So you see here a Globus flow, that data comes off an instrument. We run a QA task to make sure the data looks good. A user checks it, says it's okay. We transfer the data to Theta, now Polaris at ALCF. We do some analysis. We do some visualization to create this nice picture here of some scattering data or crystallography data. We gather some metadata. We put that all in a portal that you can see on the left, such that other people or the researchers or their collaborators can find that data, view the reconstruction, be able to do analysis or further analysis on the data. So with that, I'm done. I just want to say really quickly, thank you to all the people that have supported this, from the Department of Energy, obviously the University of Chicago and Argonne have been very helpful, and NSF, who gave us a CSSI award to make this a production system. With that, I am done, and I will take any questions.
All right, everyone. If you have any questions in our audience, please do feel free to enter them in either the chat and the Q&A, as we'll be monitoring both. And I would love to also invite back up our host panelists to see if we have any discussion points or questions for Kyle about Globus Compute or just remote computing using Python. So Kyle, I do have a question for you. And I was curious about the execution environment of the Python functions. Now the user can the user define packages and things to install in advance of the execution of this function? Or is there a subset of things, or is it like a Docker file or something they end up supplying?
Yeah, so that's a really, really great question. So of course, when you define a function that needs to be executed remotely, one of the challenging things, as I mentioned, was having the environment match what you need, the dependent modules, to be able to execute that thing. So we have two main approaches for that, both of which rely on pre-configuring an environment. One being using a Conda environment in the remote system, which of course we can remotely pip install things in that Conda environment. But typically we assume that there's a Conda environment that's compatible, or we use containers. So we have support for Docker Singularity Shifter, where we can basically run these worker processes inside predefined containers. And we're seeing, at least in the HPC world, there's pretty good support and adoption for container technologies that remove a lot of those barriers. And of course, the nice thing there is we can download these containers from public repositories or from Docker repositories, et cetera, and then use them to execute on the remote side.
That's really neat. For something, say I have, a bunch of jobs that I want to submit, how would one go about saying, I want to create the environment once, run 30 jobs in it, and then I'm all done?
Yeah, so we don't have any way to destroy the environment. So you can't go and destroy that Conda environment, but you can, basically the worker, the agent will provision resources for some period of time. There's a threshold there. Once the workload stops, we basically release the resources, release that environment back to the scheduler such that other people can run the task. Or run their tasks, use the batch scheduler, yeah.
Excellent. And Tom, I see you're off audio. Did you have a question as well?
Sorry, just a very technical question. Do you restart the Python process between each function, or if I execute the function 30 times, do they all run in the same process?
That's a really great question. So this comes from our parcel library. We've worked on both models. There are obviously pretty significant overheads to creating a Python interpreter, so starting up that Python environment. So the default model we use is to reuse that environment. So there's some implications there. Like most often that's not a problem, but of course there are implications. So Actually, we do use it sometimes as an optimization thing because you can store like a machine learning model in a global so that it's actually accessible to the next task that arrives on that worker. But of course, it relies on the fact that you're being a good citizen to yourself, as you're the one that's reusing that worker, and therefore you're inheriting any of that shared state that has occurred before you. We can also change that such that it starts up a new interpreter each time, but in practice, 99% of people will reuse the interpreter because it's just so much faster, and the security implications are minimal when it's only me that's running tasks on those workers.
Excellent. Now, Kyle, I have another question. Kind of what is or who is kind of your standard user who's interested in these types of services? Is there like specific disciplines, or is it going to be almost all different research backgrounds?
Yeah, that's a really good question. When I think through our big user base at the moment, it's really so broad. There's research software engineers that use it as abstraction layers for running computing tasks for several different types of users. So we've got a couple of big users like that. We've got some big use in material science, biology, some people studying the sun. So there's some groups that are using it for large workloads. We actually wrote a paper where we analyze. One of the interesting things is, of course, we have history in the cloud of the tasks that are being run. And so we wrote a paper where we released a data set of the functions over a 3 or 6 month period that were being run from different people. And we tried to characterize the types of functions that were being run in terms of domain. We didn't release the function bodies, of course, but we characterized the types of functions that were being run. There was a large amount of machine learning, large amount of sort of data manipulation, pandas-y types things, a lot of people actually using it to run exec a process in another language. So they weren't using it, they were using Python as like the API to open a process running Fortran or something we didn't even know about, a shell script, Fortran, etc. So those were the main uses. The other interesting thing that we found with that paper was that the runtimes were relatively short, so much shorter than a batch job. And that's where the pilot job model becomes very useful for us. So someone wants to run things that run for seconds to minutes rather than hours was a big difference.
Fascinating, and thank you for the user. I love knowing who's using what tools and how often. So it does sound, those fields, by my own declaration, right, do sound like some very large data sets that they're working with, and they don't want to compute things over a matter of months, but maybe in days.
Yeah.
So the question on that, do you find people are shipping things like a file name and then we're assuming they can find it on the runner, or are people shipping like actual data arrays into these functions?
Yeah, that's a really good question. Something I should have mentioned in the slide. So obviously we're storing data in the cloud, and we are also transferring data through the cloud. So there's egress cost that we incur. So we put a limit of, I think it's 10 megabytes per function to discourage people using this as a file transfer service. That works for sort of modest use cases, but we have one instance of a group using it for federated learning, where of course you're transferring models, and models, large neural network models, can become significant. In those cases, we see a couple of things. So one group I know was using S3, so they would basically just create an S3 connector and write everything, all the data to S3 when they finished computing, and then retrieve it from there. Another group is using Globus extensively because, of course, we're pretty tightly coupled with the Globus transfer side. So a lot of the places we're executing tasks, there's already a Globus transfer endpoint. So we can easily just access the data on the file system, and through the same SDK interface, I can then move that data behind the scenes in a direct peer-to-peer way. So I'm moving it from where it was created, where the function was run, to my laptop or to my storage service somewhere else where I want to store it. So those tend to be our go-tos. If you've got data that's bigger than a few megabytes, please use Globus transfer or something out of band, or even just leave it on the file system of the big HPC you're storing it on, because often that's where you want to keep it anyway.
Very fair. Awesome. Thank you so much, Kyle. And Tom, thank you for the fantastic questions. That was the end of a fantastic exchange. And I want to extend a huge thank you to Kyle and to our audience for joining us this month. I want to remind you, if you have not already signed up for our newsletter, well, make sure you subscribe. The subscription link can be found on our website, meetup.doepy.org. And I'll say, if you don't like receiving just one email per month, if that's too much, then you should make sure that you keep a regular eye on that same website for information about our upcoming exchange next month. Thank you all again for joining, and I hope to see you again next time.